Chapter 15 is about acid-base equilibria, and Section 1 is about solutions of acids or bases containing a common ion. Again, in this section, we will be calculating pH, determining the species that will react, and looking at the concentrations at equilibrium. Solutions of acids or bases that contain a common ion exhibit the common ion effect. This is where we add an ion to an equilibrium system that is already present in that equilibrium system. According to Le Chatelier's principle, the reaction will shift to try to react that added ion. For example, here's our equilibrium system. We have our acid, our base, our conjugate acid, and our conjugate base. And to that system, we are going to add sodium cyanide. That cyanide ion is already in this equilibrium system. So if we add cyanide ion, the reaction is going to shift to the left, according to Le Chatelier's principle. And in the process, the hydronium is going to be reacted as well. So as a result, the pH is higher. So a solution that has the acid and the common ion is going to be less acidic than the acid alone. Let's demonstrate this through calculations. In a 1 molar hydrofluoric acid solution, the hydrogen or hydronium ion concentration is 2.7 times 10 to the negative 7th molar, and the percent dissociation is 2.7%. We are going to look at the effect of a common ion if we add sodium fluoride to that acidic solution. We're going to calculate the hydrogen ion concentration and also look at the percent dissociation. So like in Chapter 14, let's think about the major species that we would see in the solution. Because hydrofluoric acid is a weak acid, we'll see mostly molecules, HF, and then from the sodium fluoride, we'll see fluoride ions and sodium ions, and then of course there will be some water. Also from Chapter 14, we know that sodium ion won't do anything, and so then our equation is going to be the hydrofluoric acid will dissociate into hydrogen ion and fluoride ion. So let's do an ice chart. The hydrofluoric acid concentration is 1 molar, and the fluoride ion concentration is 1 molar. This is different than problems that we did in Chapter 14. We still initially, though, don't have any hydrogen ion. We will complete our ice chart as we normally do, and then use the Ka in the equilibrium expression to solve for x. Notice, because Ka is so small, I turned 1 minus x into just 1, and 1 plus x into just 1. X equals 7.2 times 10 to the negative 4th molar. I checked this with the 5% rule and it was acceptable. And then therefore the hydrogen ion concentration is 7.2 times 10 to the negative 4th molar. Notice how this hydrogen ion concentration compares to the hydrogen ion concentration in just a hydrofluoric acid solution. It is much, much less in our solution that contains the common ion fluoride. Therefore, the pH would be higher in our solution that contains the common ion. We can also compare the percent dissociation in our new solution. If we compare our value to x to the original concentration of the hydrofluoric acid, we see 0.072% dissociation. Compare that to 2.7% dissociation for just a solution that contains hydrofluoric acid. The addition of the fluoride ion has shifted the equilibrium to the left, creating much less hydrogen ion and much lower percent dissociation for the hydrofluoric acid. In section 2 of chapter 15, we will be taking a look at buffered solutions, which is a very important application of the common ion effect.